A proposed heat engine produces work at a rate of 6.5 megawatts while operating at steady state. Air enters the engine at 10 bar and 600 Kelvin and leaves at 1 bar and 500 Kelvin. The mass flow rate of the air is 1.2 kilograms per second. The engine also receives superheated steam at 20 bar and 500 degrees C, which leaves the engine as a saturated vapor at 1 bar. The engine is well insulated from its surroundings, and kinetic and potential energy may be neglected. Assume that air behaves as an ideal gas with R equals 0.287 kilojoules per kilogram Kelvin. Is the power output claimed possible? So this is a classic second law problem where we're trying to prove or disprove a claim of power produced by a heat engine. So we'll take a look at our given information. We have a schematic diagram here. Notice that this is just described as a proposed heat engine. We're not told what components are in this heat engine, so we're just going to represent it schematically by this box. It doesn't matter what's inside of this box. But what we are told is quite a bit of information about what is entering and leaving the box. So we've got air entering at 1 and leaving at 2, and we've got water entering at 3 and leaving at 4. So our control volume here is going to have 2 inlets and 2 exits. Properties that were given at these state points: the air inlet is 10 bar and 600 Kelvin, and its exit is 1 bar and 500 Kelvin. And the mass flow rate of the air is 1.2 kilograms per second. So I'm calling that m dot 1, but of course m dot 2 will be the same. For the water, it comes in at 20 bar and 500 degrees C, and it leaves at 1 bar and as a saturated vapor. So notice all 4 of these state points are fixed. We know enough information at all 4 of those points to look up any property that we need. Other things we're told here is that this machine is producing a shaft power of 6.5 megawatts. And in fact, what we're doing here is trying to figure out whether this is possible or not. Finally, we're told that the system is adiabatic. There's no appreciable heat transfer between this thing and the surroundings. So just to state what we're asked to find, is it possible for this heat engine to produce 6.5 megawatts? And like I say, this is a classic second law problem where we're trying to prove or disprove a claim of the power produced by a machine. Well, the assumptions we'll make in this analysis: steady state operation, adiabatic, and neglect kinetic and potential energy. So we're interested in finding the power produced by this machine. So the approach we're going to take here is to just set aside the 6.5 megawatts for a while, pretend that we weren't given that, and just see if we can calculate the maximum possible power that this machine can produce. So we'll be getting that power from the energy balance. So we'll begin with the conservation of energy equation for a control volume. So here we're showing the complete equation, but if we assume steady state, this term is gone. Adiabatic system, heat transfer term is gone. We're trying to solve for this shaft work, so we certainly keep that. We need to be careful with the inlets and exits, and we need to realize there are 2 inlets and 2 exits. But for each of those, we can neglect kinetic and potential energy. So when we apply those assumptions to our control volume, this equation becomes W dot, the power that we're trying to calculate, is the mass flow rate of the air times the air inlet minus the air exit enthalpy, plus the mass flow rate of the water times the water inlet enthalpy minus the water exit enthalpy. So that's the simplified version of this equation for this problem. Now if we take a look at this, we actually have enough information to find all of these H's. And we were given the mass flow rate of the air. But the problem we have is we don't know the mass flow rate of the water. So there's enough information given to fix the state at all the inlets and exits, but the mass flow rate of the water is not known. So we'll have to set this equation aside for a moment and find the mass flow rate of the water. And the way we do that is with an entropy balance. So we apply our entropy balance to this heat engine. Again, it's steady state, so that term will be 0. It's adiabatic, so this is 0. And because we're trying to figure out the maximum possible power that it can produce, the entropy production term here will also be set to 0. So when we do that, we still need to be careful because there are 2 inlets and 2 exits. But when we do that and rewrite the equation, we will get a mass flow rate of the air times S1 minus S2. That's the air inlet and the air exit. And the mass flow rate of the water times S3 minus S4, the water inlet and the water exit. Now, because air is an ideal gas, we can calculate this entropy change from the change in the S0 values, that's the temperature-dependent part, minus R times the log of P1 over P2. So this accounts for the pressure change. The entropy change for the water we'll be getting directly out of the appropriate tables. So in this equation, the only thing we don't know is the mass flow rate of the water. So we'll look up all of these properties and calculate the mass flow rate of the water. So the air properties are going to come from an ideal gas table for air. That's table A22. So at state point 1 and 2, which are at 600 and 500 degrees Kelvin, we have our value of H and our value of S0 taken out of that table. For water, we can go to table A4, and at 20 bar and 600 degrees, we get our value of enthalpy and entropy directly out of table A4. And at 1 bar, we can get the saturated vapor values out of table A4 as well, and that's this value of enthalpy and this value of entropy. So now we have everything in that entropy balance except the mass flow rate. So we can substitute these numbers into the entropy balance and solve for this mass flow rate. And m dot 3 comes out to 7.8231 kilograms per second. Now we can go back to the first law, because now we've solved for this mass flow rate and we looked up all 4 of these enthalpy values, so we know everything on the right-hand side of this equation now. So substituting all of that in, mass flow rate of the air times the enthalpy change of the air plus the mass flow rate of the water times the enthalpy change of the water. And that works out to 6321.5 kilowatts or 6.32 megawatts. Now remember, in order to get this number, we set the irreversibilities to 0 in the entropy balance. In other words, we said we're going to look at a perfect machine. So this is the maximum possible power that this machine can produce. Well, the claim of power was 6.5 megawatts. So that means that's impossible. The maximum is 6.3. There's no way this machine can produce 6.5. So our conclusion would be it is impossible for this heat engine to produce 6.5 megawatts.